Hi all, welcome to the lecture series on solving previous year questions from GATE ECE, and we were solving the op-amp related questions from the subject analog circuits. Yeah, so let us start. So today this is the first question from GATE 2020. The question is, the component in the circuit given below are ideal if R equal to 2 kilo ohm and C equal to 1 microfarad. The minus 3 dB cutoff frequency of the circuit is in hertz is. So the question is, a filter is given here, and the question says like to find the 3 dB cutoff frequency. Okay, so let us analyze the circuit and we'll see what sort of filter is it. Okay, so here there is an RC network at the input, and we have an RC network here also at the output, or we'll say like at the feedback. Okay, and from the circuit it is clear that it is a negative feedback system, right? Because the feedback voltage is given to its inverting terminal and non-inverting terminal is connected to ground. Okay, which means this is 0 volt. So it's a inverting configuration, so definitely this node will be having 0 volt. Okay, virtual ground. So which means if we carefully see here, this resistance, that is resistance having the value 2R, its one node is connected to ground and the other node is connected to virtual ground. So it is like effectively there is no current flowing through this, right? The current flowing through this resistance is 0 ampere, or it is like we have not connected any resistance. Similarly, this capacitance also, this node is connected to ground and this node is connected to virtual ground. So here also the current to the capacitor is 0 ampere. So I can effectively draw the circuit, redraw the circuit like this. Yeah. So this is minus, this plus. Okay, so we have removed the capacitor 2C and 2R, and we have resistance R here, C here, and Vi. Okay, so what is this circuit? This circuit is a low pass filter. That is, when the frequency of Vi is high, this capacitance C will be short circuited, right? Because the impedance will be low across the capacitor. As such, the feedback will be short circuited and the gain will go down. Okay, and when the frequency is low, this capacitance will provide very high impedance, and thereby at low frequency the gain will be high. So it's a low pass filter, and what will be its cutoff frequency F? The F will be equal to 1 by 2 pi the resistance R into C, capacitance. Okay, so I'll substitute the values given. R is 2 kilo ohm and the capacitance is 1 microfarad. Fine, and if we substitute this, we'll get the value as 79.58 hertz. Okay, so the answer is D. Yeah, so that was the first question. Now let us see the second one. This is from GATE 2018. The question is, an op-amp based circuit is implemented as shown below. So this is the circuit, and in the above circuit, assume the op-amp to be ideal. The voltage in volts correct to 1 decimal place at the node A, that is this node, connected to the negative input of the op-amp as indicated in the figure is. So the question is like, as you can see, it's a inverting amplifier, right? And where there is an input resistance of 1k, and at feedback we have 31 kilo ohm, and this node A is connected to the inverting terminal of the op-amp. So question is to find what is this voltage at A. Okay, since it's a inverting configuration, definitely we will feel that since this is 0 volt, this may be 0 volt because of virtual ground concept, right? So we will just analyze that. Okay, in that case we will analyze. So here the Vi given is 1 volt, and it's a it's an inverting configuration. Okay, inverting amplifier. Okay, so what will be V naught? V naught will be equal to minus Rf by R1 into Vi, right? So minus Rf here is 31k and R1 is 1k. So I will put like minus 31k by R1 is 1k, that into 1. Okay, so this will be equal to 31, right? Minus 31. Yeah, so V naught is minus 31. Now if you carefully see here, so I will just draw this circuit again. (31k), 1k, V naught, (1 volt), okay, and the bias supply is plus 15 and minus 15. Okay, so V naught equal to minus 31, it is not possible, right? Because this op amp will have a characteristics like this. Okay, it can't go above, oh sorry, it's a inverting configuration, so I should not draw like this. I will draw like this. So Vi, if it is positive, output should be negative and it saturates, yeah, like this. Okay, so which means it will saturate, even though in ideal case we will say like V naught is equal to the gain into the input. There is always a limit, it can't, the output voltage cannot go above its saturation voltage. And what is the saturation voltage? Since if it is ideal, this will be minus 15 and this will be plus 15. So V naught cannot go above 15 or minus 15. So definitely the V naught will saturate and the value will be equal to minus 15. Okay. So from the circuit, what will be Va? So if this is saturated minus 15, so what happens? Va, the voltage at A, will not be equal to 0 now. Okay. So how to find Va now? So we will apply the KCL. So this is Va at node A. At node A, we will apply KCL. So Va voltage at A minus 1 by 1k plus Va minus V naught, so by 31k is equal to 0. Okay, so I will substitute Va minus 1 by 1k plus Va, V naught is now 15, right, minus 15, so minus it will be plus 15 by 31k equal to 0. So I will take I will combine the values of Va, so it will be Va into 1 plus 1 by 31 and the remaining terms I will take to the RHS, so it will be 1 minus 15 by 31. Okay, so Va into 32 by 31 is equal to 31 minus 15 by 31. Okay, so what will be Va? Va will be equal to 31 minus 15 is 16 and that by 32. So this is 1 by 2 or it is equal to 0.5 volt. So Va is actually 0.5 volt, not 0. Okay, so answer is 0.5 volt. Yeah. Okay. Okay, so let us see the next question. So this is from GATE 2018. So the question is, in the circuit shown below, the op amp is ideal and the Zener voltage of the diode is 2.5 volt. So there is one Zener diode here and the Zener voltage of that diode is 2.5 volt. At the input, the unit step voltage is applied, that is V in of t equal to U of t. Also at t equal to 0, the voltage across each of the capacitor is 0. So this is the circuit and we will see what is the question. The time t in milliseconds at which the output V naught crosses minus 10 voltage. So the question is like, we have a circuit where two capacitor is kept at its feedback, and definitely if voltage is applied, okay, step voltage is applied, the voltage across the capacitor won't rise quickly, right? So there is some transient. So at what value of time, or at what time the Vout will reach minus 10 volt? So that is a question. So we'll see this. So initially, given initially at t equal to 0, capacitor or capacitors are discharged or are at zero potential, right? Okay, so I can draw the circuit as minus plus okay, so this is V naught, and since initially the capacitor across the capacitor the voltage is 0, we'll say the Zener diode is open circuited, right? Because it require a minimum of minus 2.5 volt plus 2.5 volt across the Zener to have that voltage across that Zener diode, right? So we'll consider that to be open circuited. So this is 1 kilo ohm, and a voltage, step voltage is given at t equal to 0, and the amplitude is 1 volt. Okay, so this is C1 I will say, and this is C2. Okay, so if 1 volt DC voltage comes after t greater than 0, what will the current through this resistor? That will be equal to 1 volt by 1k, right? Because this is 0 virtual grounded. So this is equal to 1 milliampere. Okay, so 1 milliampere current is flowing, and the same current will flow like this. Okay, I will call it as I. Okay, so when this flows like this, there will be a voltage building up, or the capacitor will charge. So there will be voltage building up across the capacitor like this, plus minus plus minus. Okay, so the voltage across this capacitor C1 I will call it as VC1, and across C2 I will call it as VC2. Okay, so what will the capacitance voltage VC1? That will be equal to 1 by C1 integral 0 to t, okay, for some time t, current flowing through the capacitor I of t, okay, dt, or we'll take the dummy variable as tau, okay, or integral variable as d tau. Okay, so I'll substitute the values. So capacitance given is, the capacitor value is 1 microfarad. So 1 microfarad integral 0 to t. I of t now is actually a constant, right? That is equal to 1 milliampere. So 1 milli d tau. Okay, so 1 milli by 1 micro is like 1 by 1 milli. Okay, and if I integrate this, this is tau from the limit 0 to t. Okay, 1 by 1 milli is 1000, so it will be 1000 into t minus 0, that is t. So 1000 t. So VC1 is equal to 1000 t. Okay, now if you carefully see, the same current I is flowing through C2 also. Okay, so what will be VC2? VC2 is also equal to 1000 t. So VC1, both VC1 and VC2 is actually 1000 t. We know the as the current flows, the voltage VC2 and VC1 increments, right? So I can draw like this. So if this is the t, and if this is VC1 or VC2, the voltage will increment like this with respect to time. And what is the slope? Slope will be equal to 1000. Okay, so at what time t, okay, VC2 will reach equal to 2.5 volt, because the capacitance voltage, this voltage is actually falling across the Zener, right? The same voltage is falling across the Zener diode. So when the capacitance voltage of C2, this capacitor reaches 2.5 volt, the Zener will be on, I mean reverse biased. Okay, and the voltage across the Zener will be regulated to 2.5 volt, right? So we'll see at what time this voltage VC2 reaches 2.5. So I know VC2 is 1000 t, and this is equal to 2.5. So t is equal to 2.5 by 1000, that is 2.5 millisecond, which means at t equal to 2.5 millisecond, the capacitor voltage Vc2 will be equal to 2.5 volt. Okay, so what happens, I will redraw the circuit again. Capacitor like this, there is capacitor and there will be zener here, and since this reaches 2.5 volt, that will be maintained now, right? V0, the voltage across the zener will be now maintained. Okay, and here it is like 2.5 volt reached at t equal to 2.5 millisecond plus Vc2, the changing Vc2 will be there. Okay, that is Vc2. Okay, or I will just simply tell it is as Vc2 itself. Okay, so R 1 milliampere and Vn. Okay, so at t equal to 2.5 millisecond, what will be V0? V0 will be equal to minus of this voltage, right? Vc2, sorry, this is Vc1, sorry, this is Vc1. So minus of Vc1 minus this is Vc2. Okay, minus of Vc2, or minus of Vc1 plus Vc2 is the V0, right? So here what is Vc1 now? At 2.5 millisecond, Vc1 is 2.5 volt and Vc2 is 2.5 volt, so 5 volt. Okay, so at 2.5 millisecond, the voltage reached, V0 reached is minus 5 volt. But the question is to find what is the time at which the voltage reaches minus 10 volt. Okay, now what happens for t greater than 2.5 millisecond? What happens? V0 will be equal to minus Vc1 plus Vc2, right? So minus Vc1 is 2.5, I will say like 2.5 plus some delta Vc1, that is again the Vc1 will definitely change while Vc2 will remain constant. Vc2 is 2.5 volt itself. So at 2.5 millisecond, Vc2 is 2.5 volt because the Zener diode has attained the breakdown, right? So we can write it as minus 5 plus delta Vc1. Okay, minus of 5 plus delta C1, that is V0 after t greater than 2.5 millisecond. Now question is, when does V0 equals minus 10 volt? When does this V0 reaches minus 10 volt? So we will substitute in this equation. It will be minus 10 equal to minus of 5 plus delta Vc1, where delta Vc1 is the remaining voltage change in the Vc1. Okay, 2.5 plus delta Vc1. Okay, so minus cancelled, so it will be like 5 equal to delta Vc1. When does the capacitance C1 reaches the value 5 volt? Okay, after 2.5 millisecond. Okay, so what is it delta Vc1? Delta Vc1 is the voltage across C1 itself. So that is, this will be equal to 1000 T itself. Okay, because the same current is flowing and there is no Zener or any other element across this capacitor C1. So the Vc1 or the voltage across the capacitor C1 will increment linearly. Okay, so I can write 5 equal to 1000 T or T equal to 5 milliseconds. So it will take the next 5 millisecond for Vc1 to reach the voltage 7.5. So 7.5 plus 2.5 is 10, right? So it require more 5 millisecond so that V0 will be equal to 10. So therefore V0 will be equal to 10 volt when for how much time? That is initial 2.5 millisecond plus the remaining 5 millisecond, that is it will require 7.5 millisecond for the V0 to attain 10 volt. Okay, yeah. So the answer is C, 7.5 millisecond. Thank you.